Today's speaker is Dr. Michael Dodds. He is currently a Director of Consulting Services at Certara. Before coming to Certara, he worked at Zymogenetics and Amgen. Mike is a pharmacometrics subject matter expert, and he has authored more than 20 peer-reviewed articles. He earned his bachelor's degree in chemical engineering and a bachelor's in biochemistry from the North Carolina State University. He then went on to earn his master's degree in chemical engineering from the Montana State University and a PhD in bioengineering from the University of Washington. Mike, welcome to today's webinar. I'll now turn it over to him to begin the presentation.
Thanks, Suzanne, and thanks for the kind introduction. Could you pull up Menti, and I can ask our first question, which is, are you using modeling and simulation to support vaccine development? My bias going into this presentation is that no, we're really not using modeling and simulation to help support vaccine development. As I was going through literature to figure out how the timing of vaccines is determined, I didn't find a lot out there. However, there are some individuals on the call that are using modeling and simulation. That would be very interesting to know. I strongly suspect that there are very few of us out there. Typically speaking, the choice of vaccination timing, at least in the context of infants, are very much scheduled around bringing those kids in for routine checkups, well child, that sort of business. So there isn't a whole lot of opportunity, at least that I'm aware of, to really think about is that schedule optimal. And as we go through the presentation today, I think I can demonstrate that our choice of recommendation for vaccinating mothers during pregnancy for influenza is quite possibly not optimal. Well, we've got a few responses here, and I won't do the math quickly, but this seems to confirm my bias that yeah, we're not using modeling or simulation approaches very much to assist in vaccine development. Suzanne, let's have the ball back. Thanks. So, as some background, the maternal vaccination policy in the United States is set by the Advisory Committee on Immunization Practices. That's ACIP, and it's a branch of the CDC. And they recommend that pregnant women be vaccinated with a variety of vaccines. The two that I'm going to speak to today are tetanus, diphtheria, and pertussis. That's the Tdap, and then influenza. So that's the inactivated influenza vaccines. In the case of Tdap, there's an express recommendation to maximize the maternal antibody response and passive antibody transfer to the infant. And the ACIP recommends that the Tdap administration be given during between 27 and 37 weeks or 36 weeks of gestation. In influenza, it's different. The recommendation is that the vaccine be administered at any time during pregnancy. So two different recommendations here. There are risk-benefit approaches that are recommended for other vaccines, and the ACIP steps practitioners through that, but there really isn't any specific guidance for timing. Okay, so that's kind of the backdrop of recommendations for when mothers should be vaccinated. Why would we want to vaccinate mothers? Well, typically we vaccinate children for influenza at 6 months of age. Until that point, those infants are really relying on transferred antibodies, and typically those are IgG from the mother via the placenta. That transfer is dependent on a number of factors. The two that are going to be important for today's discussion are maternal levels and gestational age. So in general, the maternal levels of total IgG and then specific antibodies, those infant levels are approximately maternal levels, at least at birth. When that ratio isn't one-to-one, we talk about transfer efficiency of why these antibodies, some are preferentially transferred or some are not. The other component that's important is gestational age. We know that the majority of the antibodies are transferred in the last 4 weeks of pregnancy. The other components then are sort of placental integrity, different IgG subclasses are differentially or preferentially transferred, and then the nature of the antigen, whether it's thymus dependent or not, often impacts that, that transfer. The important point here is that the maternal levels and gestational age are both time-dependent components, suggesting that the recommendation from ACIP that we give vaccine, the influenza vaccine any time during pregnancy may not be optimal. And in fact, the experience with the Tdap vaccine strongly suggests that timing does matter. We learned from the initial poll that modeling simulation is not at least widely deployed in the vaccine space. So I thought it important today to step you through sort of the causal chain of events and the thinking that went into this analysis. It's not like this is a well-hoed row. We should apply the same critical thinking that we've done for traditional model-based drug development and really think about those precepts as we're working through the supporting vaccine. So in kind of the classic engineering sense, stepping through the causal chain, we begin with vaccination. We know that vaccination leads to maternal antibodies. The first question then that comes to mind is, well, what are the kinetics of the antibodies in mom? Are they flat and unchanging with respect to time? Did they go up? Did they go down? How fast? Further, can we leverage information about humoral immunity? We know we're employing the immune system to generate these antibodies. What is known about that humoral immune system, and can we use that and leverage that information in the context of limited antibody data? The next step then is if we understand the maternal levels of antibodies, we understand that those and the infant's gestational age impact the infant levels at birth. So that begs the question, well, is there a peak in those antibody levels, and when does it occur? The other component we need to be mindful of is a special population. We know that this antibody transfer happens mostly in the last 4 weeks before delivery. So if these preterm infants have lower antibody levels, do we need to make an adjustment in our recommendation to the maternal vaccination timing to better protect this subpopulation? At the risk then we give up a little bit of efficacy on the term infant side, but generally those preterm infants are at a much higher risk. Once we've understood how the antibodies are delivered to the infant at birth, we know that the antibody levels wane in those infants after birth. And that leads to a similar line of inquiry that we did for mom. What are the kinetics of those antibodies in the infants? How fast do they wane? And importantly, can we leverage information about antibody kinetics to gain greater insight with limited antibody data? After all, we've been developing antibodies as therapeutics for multiple decades. Surely there must be some useful information in the literature to assist us in this task. Finally, once we have an idea of what the infant antibody titers look like, we'd like to map that to protection. Right? We know that those waning antibody levels convey protection to the infants, but at some point the efficacy begins to drop off. And this is very similar to the same sort of analysis we do on a drug concentration pharmacodynamic effect. Right? At some point we believe there's a threshold of drug concentration, or in this case antibodies, below which the vaccine provides less protection. That's outside of the scope of this presentation, but that's the ultimate goal of these efforts, the kind of thing we're working towards. So that's the causal chain, and I'll return to that and begin stepping you through each of these stages. I'm fortunate to be working with the Bill and Melinda Gates Foundation, who are collaborating with the Maternal Influenza Immunization Working Group. And this is a large multinational group that conducted prospective studies in 3 different geographic regions. to assess the efficacy of maternal vaccination. What I'm trying to show you in this slide is the different protocols, the different study setups. The two data sets that I'm going to use to train the model are the Mali and the South Africa trials. I'm going to hold the Nepalese data in reserve for an external validation step. What I'm trying to show you on this plot is on the x-axis time relative to delivery, so 0 would be the time of delivery of the infant. The blue dot and blue interval gives you the protocol-defined time when these mothers were vaccinated. So at the top of the plot from Mali, you can see that the vaccination was really taking place in the mid to late portion of the third trimester. The trimesters are highlighted by vertical dashed lines. In contrast, the South African trial, the vaccination window was really at the end of the second trimester and the beginning of the third trimester. And again, in contrast, in Nepal, the vaccination is happening even earlier. So we've got differences in these vaccination schedules. You can also appreciate the sampling schedule from this plot. The serum draws from mom appear in orange, and the sticks from the infants appear as black dots. So we know going into this analysis that we've got relatively sparse data, and we're going to have to leverage everything we can from literature to work with this complicated system. So the primary objective of this analysis is, can we leverage these data to determine the optimal vaccination time? The clear differences in the protocol specification, we have windows of vaccination. Can we leverage this sparse data, but in thousands of mother-infant pairs, to get a sense of when is the optimal time, if any, to vaccinate mom? Okay. So starting through that causal chain, we know that vaccination gives rise to antibodies in mom, right? So what happens? How does that happen? Well, we know that antibodies are produced in by plasma cells, and plasma cells require time for recruitment, differentiation, population expansion. Once we have those plasma cell populations, realistically, we have two populations that we need to consider, and this is an approximation, of course. We have plasma cells that are so-called short-lived. They have a very rapid turnover in the body at a half-life of around 3 days. Again, we can get this information from literature values. We also have a population of plasma cells that are so-called long-lived. They have a half-life of approximately half a year. So we've got these two different populations that are then going to start producing infusions of antibodies into mom's bloodstream. Once produced, those antibodies have a half-life of around 21 days in adults. And again, we know that from decades of drug development for antibodies. So this gives rise to a relatively simple structural model that has vaccination, then recruiting, differentiating, expanding B cells. And we use a Stirling approximation to work through a similar sort of deal when you're trying to go through oral absorption with a bunch of different kinetics. You can use that relatively flexible shape to characterize the time it takes before these plasma cells are producing antibodies. Once we have those plasma cells, we have a pool population of these cells that are then producing antibodies, and they have two different, very different half-lives. Those then produce antibodies that we can then measure in mom, and those antibodies are also turning over at a kinetic rate with a half-life of 21 days. So a relatively simple structural model, and you'll note that we're informing many of these parameters from literature values. These are the fits to the maternal antibody data. To walk you through the layout of these panels, the South Africa trial appears in the left panel. The Mali trial appears on the right. Again, I'm withholding the Nepalese data for a validation step. The x-axis is relatively simple to explain. That's time after vaccination in units of weeks. And the y-axis is relatively complicated to explain. So I'm going to resist the urge to dive into technical details, but the way these assays are configured, these studies were not run at a central lab. Each study had their own central lab. But the way these antibodies are assessed is through an initial dilution of the sample, which is different across trials, and then serial dilution until such time as the sample doesn't block a signal in an in vitro assay. So what you're getting is you're diluting the sample by a certain factor each time, and so you end up with 1 dilution, 2 dilutions, 3 dilutions. At some point, the antibody begins to fail. Those dilution values are then reported, 5 dilutions, 6 dilutions, 7 dilutions, and that's what we're looking at on the y-axis. So it's digital data, if you will, or ordered categorical. The data itself, we have a limited and sparse sampling schedule. I've color-coded it based on visits. So the first visit, which is prior to vaccination, appears in black, and so on. It's a relatively heterogeneous sampling schedule, but I've tried to color-code things according to visit. The data itself are summarized by visit using box plots. The median of the data appears as a horizontal line in each of those boxes, and then the 5th and 95th percentile of the data appears as the extent of the box. The model fits appear as a blue line in a blue envelope. The solid blue line is the median of the prediction, and what you'd like to see is the median of that prediction lines up with the median of the data, horizontal crossbars in the box plot. And then the variation, the variability, and uncertainty in the predictions appears in blue envelope, and you'd like that to coincide with the edges of the box plots, essentially. So in general, I would argue the model adequately captures the baseline, the rise, and the fall of these maternal titer values. We get from that some knowledge. We understand that it takes 20 days to begin to recruit these plasma cells to start producing antibodies. We can also look at other aspects of the kinetics. We can do some simulations and find that over a year, 85% of that titer is produced by that long-lived plasma cell population, and that makes sense, right? The short-lived plasma cells have a half-life of 3 days, so they're in a sense a flash in the pan, but they do produce a pretty strong amount of antibodies right off the bat, and so over a time span on the order of weeks, this might be a very important cell population, right? Still working through a covariate search because you can see that there's a great deal of heterogeneity in the data. But that's kind of outside of the scope of today's presentation. We can use that model then in simulation mode to do a couple things. First, we can lay out a much more fine, granular time axis. So again, we're looking at time after vaccination on the x-axis, and now we can look at much more granular time points. And you can see from that we're predicting that we have a relatively low titer level. And then there is a pretty dramatic increase, but it is lagged by 20 days or so. We then arrive at a peak, and that peak occurs somewhere in the 7 to 9 week time period, and then slowly the antibodies wane, and that waning is both the turnover of the antibody itself, but it's also the turnover of these plasma cell populations in the background that are producing an infusion of antibodies. The other thing we can do with the simulation is then compare it to that Nepal data set, right? I told you I held that data set aside, didn't look at it as we were going through the model fitting exercise. In that study, we had a much sparser sampling schedule. We also have less information at the subject level. But we can at least look at the medians of baseline, and we can look at the medians at a little after 13 weeks after vaccination, and get a sense that the model is doing a pretty good job predicting a study for which the model wasn't trained, right? So that's an important validation step working through this analysis. The other comparison that we can make, I introduced at the beginning the Tdap vaccine, and again, the story there is ACIP is recommending that the Tdap vaccine be administered between 27 and 36 weeks of gestation. Interestingly, Eberhardt and others conducted a prospective study after the recommendation in 335 women, and they were randomized to be immunized in the second and the third trimester on a kind of a 2-to-1 ratio. And they concluded that the early second trimester produced more infant titer. I went to that publication and pulled out from the supplemental materials their titer values that were tabulated. So what you're looking at is in the first 3 columns of this table, the Tdap infant anti-pertussis titer, and then there's multiple components to this vaccine, the anti-FHV titer in the 3rd column. These authors divided the time interval between vaccination and delivery into 15-day segments. And so you can kind of see that the distance and time between vaccination and delivery is increasing as we go down the table. And then I've used a yellow highlighter just to sort of highlight when did we see maximum infant titer for the anti-PT and the anti-FHV components. And they do differ, but they're in the range of 30 to 60-day interval between vaccination and delivery. I can look at that relative to the model predictions now. That's the final column in italics for the influenza vaccine, so a completely different vaccine. And again, we get a similar set of predictions that in that 30 to 90-day interval, we have the highest vaccine titer. So, so this does match, these 2 components match, right? The simulated maternal TIV titer suggests that the maximum titer is achieved 7 to 9 weeks or 49 to 60 days after vaccination, and this does closely match the infant Tdap titer optimum reported by Eberhardt et al. For the Tdap vaccine. Suzanne, let me turn it back over to you to pull up Menti again. I wanted to pause and poll the audience. Were you surprised by the alignment of the TIV and the Tdap titer kinetics? And I think the more provocative question is, what's going on here? Is this, both of these vaccines are utilizing the same humoral immunity system within the body to produce these antibodies. We've got 2 vaccines now that seem to have a very similar kinetic pattern, both reaching peak titer at around 8 weeks, thereabouts. To me, this is a very provocative finding. Does that mean that many vaccines have this characteristic? Is this just a fluke by chance these 2 happen to? And if we ran this question down and did find that we had a very similar kinetic pattern, does that give us a jump start on making much more precise recommendations around when we should be vaccinating mom? Because if this played out as a consistent pattern, that would strongly suggest that a maternal influenza program should have all these vaccines roughly in the 6 to 8 weeks prior to delivery. All right, well, we've got a relatively divided audience on this part. It'd be interesting to dig in the Q&A session how people feel about this point, because I think it could be a really important development for vaccines. Suzanne, let's have the ball back, and I'll keep going. Thanks. So I hope I've convinced you at this point that we have a reasonably good understanding around the maternal antibody kinetic profile, right? How does it change with respect to time? The next step in the causal chain is, well, how does the infant-maternal antibody ratio look at birth, right? Is that consistent? Can we predict it? How does that work? And generally speaking, what we find is that the antibody titer is highly correlated with maternal titer at birth. It's roughly 0.9-fold, or 1. The maternal antibody titer is given on the x-axis of this plot, and the infant level given on the y. if they were perfectly aligned, all of these dots would appear on the diagonal line. They don't. Again, this is sort of digital or ordered data, so I'm showing you by size of the circle the number of data points that have that corresponding maternal-infant titer pair. And you can see that they do line up pretty well. There are some discrepancies and some differences between these two studies, but generally the correlation is pretty tight. If we use the model to make some predictions around infant birth titer, that's on the x-axis, and the observed infant birth titer, that's on the y-axis, we get reasonably good alignment, right? So we can use that maternal antibody level to predict what the infant antibody level is at delivery. We're still working through the covariate search here. What makes one infant have more or less titer than their peer? One component that's come up is the durability of the maternal plasma cell response and the amount of maternal short-lived plasma cell response. I told you there was this relatively short-lived or flash-in-the-pan population, but something about the strength of that population's response seems to correlate with higher titer for these infants at birth. Right? So again, still working through the covariate search, but we at least have a pretty good idea at the population level how the infant and mother titers compare at birth. So that's the next step of the causal chain. We have a sense of what the infant titers would be at birth at any particular time after we vaccinate mom. That's kind of equivalent to knowing the drug's initial concentration, right, the C0 value. In this case, though, the antibody is fully distributed throughout the tissues in these infants, but we have information around what their starting antibody titer is. We know that these antibodies wane after birth. These kids don't have a plasma cell population to produce de novo antibodies. They're not getting them from mom anymore, so this really is just elimination, right? How fast do these antibodies turn over in kids? And for that, we can turn to some population pharmacokinetics work that was done for palivizumab in adults and children. They described the pharmacokinetics of palivizumab, an antibody, by a two-compartmental model, which is very similar for more or less every other antibody that we've studied. The important component about this antibody is it was extensively tested in infants because that's the target label population. So it gives us a great deal of resolution around covariates and how things impact antibody clearance. They found that clearance in children were affected principally by two components, body weight, and we've known about that for a long time. Antibodies generally, their clearance does change with body weight. And then another component, which was gestational age and postnatal age, and that's novel. The plot that I've reproduced here from Robbie, the right side of the slide, gives the baseline page in units of weeks relative on the x-axis relative to their baseline clearance on the y-axis. All of the adults are on the far right section of the plot, and then the blue line leading left is the expected clearance just based on allometry and body weight, right? So clearance goes down as the age and weight, importantly, of these kids go down. The interesting portion of this curve is right at the bottom left. You can see that all the data is beginning to deviate and quite strongly below the predicted baseline clearance simply based on body weight. In fact, the authors went through and calculated that for a full-term 40-week infant, the clearance is expected to be around 40% relative to just based on the body weight alone. So something about these very young kids are having them clear the antibody more slowly. One could speculate that perhaps a survival advantage would be conferred on an infant that retained mom's antibodies for as long as they could before they developed their own humoral response. But in this particular case, we're going to adopt the POP-PK model from palivizumab to describe the waning antibodies in infants. We're going to take that information from other pharmacometrics applications and apply that to understand what's going on with these antibodies in infants. When we do that, we can go through some data fitting exercises. So I'm showing you the same kind of plot layout as in the fits to the maternal kinetics. The profile here is quite different, right? The x-axis is different. It's time after birth in units of weeks. So the kids start out with an initial antibody concentration that's relatively high, and now the antibody is simply clearing in this population. Again, the Mali data is on the right, the South Africa data is on the left, and I've taken each of these visits where we've got a much smaller amount of data, color-coded them, and again summarized the data by 5th, 95th, and 50th percentile. The model fits are given with a similar summary, 5th, 50th, 95th, and what we'd like to see again is that solid blue line goes through the crossbar of the box plot, and that the interval of the blue envelope is approximately that of the infant observed intervals. Generally, we get a pretty good fit to the data. Without their own plasma cells, the implication is that the antibody kinetics in infants follow first-order elimination, just as if we had injected an antibody at delivery. However, the half-life is quite different. It's more like 40 to 50 days, not the 21 days that we expect for an antibody in an adult. And again, that's due to this post-gestational age and it's due to their body weight. Those of you with keen eyes will notice a clear discrepancy on the right side of the plot for the Mali data in green. For whatever reason, those infants display a pretty profound uptick in antibodies, and that seems to be happening in the majority of that population. What's going on there is in that study, that week 26 data includes infants with natural immunity. In other words, they're getting influenza infection, and what we're seeing here in the data is an observed rise in antibody titer due to infection. Okay, the model contains nothing about infection, so that's going to, of course, make the model fit be pretty poor at that time, and that's also contributing to a relatively large interval of uncertainty in the model parameters. So you could appreciate with the relatively broad blue envelopes. So we have a pretty good idea now around, given the infant's antibody levels at birth, what are their antibody levels going to look like with respect to time? And that kind of brings us to the ongoing work or future work for this exercise, which is then linking that titer level in the infant to protection. I've excerpted a nice plot from one of the investigators in this study, where they're looking at titer. I've sort of highlighted that. You can kind of see the y-axis for that appears on the right side of the plot, where they're giving geometric mean titer. It's on a normal scale, so it kind of looks like a decaying exponential, as it should. If I log transformed it, we get a relatively straight line. And what they're showing is at particular time points, the summaries of titer at those particular time in terms of the age of the infant. The protection or the efficacy against H1N1 infection appears on the left axis, and then the data itself appear as a sort of a color. I've color-coded their protection, but begins at around 70%. By the time we get to 2 to 3 months of age, it's dropped to around 50, and by the time we get to 4 to 5 months of age, it's dropped down to 10, right? So very clearly, we can now look at that titer value and kind of say, well, all right, then as that titer level is falling, there's probably a critical threshold below which that titer doesn't afford protection anymore. And this is a similar kind of pharmacometric exercise that we go through trying to establish the EC50 of a drug, right? So we're continuing to collaborate with the Maternal Influenza Immunization Data Analysis Working Group to kind of work through this protection titer relationship. if that's successful, then what we've got is a sequence of events starting from vaccination in mom and when she gets vaccinated, that then leads all the way through to some quantitative assessment of the protection that is offered to those kids with respect to time. And working backwards through that causal chain, we can run a variety of simulations to permute all the possible times that we could be vaccinating mom, and then look at those protection curves for kids. And from that, figure out what is the response curve of protection relative to mom's vaccination time. Okay, so that's kind of where things are heading there. So let me summarize. Maternal antibody production follows from humoral immune response biology. You saw the quantity of data that we're working with. It's just not possible from that relatively sparse data to fully characterize a model like this. But we can leverage literature. We know that these short and long-lived plasma cells appear after delay. They generate an infusion of antibodies. And the maternal antibody kinetics that we're observing are some net of plasma cell production, which you can think of as a constant infusion, and the antibody turnover, and that's common to IgGs and antibodies themselves. The one difference is, imagine that infusion is slowly dialing down over time as these plasma cell populations die off. From there, we can work through the infant levels at birth, and those are highly associated with maternal levels. Still working through a deeper covariate search to elucidate the effects of gestational age. We can't control gestational age at birth, right? That's going to happen the way it happens. But we do need to factor this into our thinking to understand whether we need to somehow adjust our recommendation to factor in this potentially preterm infants that are also at greater risk of respiratory infection. Finally, antibody levels wane after birth. Those antibody kinetics are very similar to those observed for palivizumab, where increasing weight and postnatal and gestational age begin to increase clearance. And again, you saw the relatively sparse data that we were working with. It's really not possible then to sort of characterize all of those different effects with that relatively sparse data, but we can borrow information from other pharmacometrics efforts in model-based drug development and bring them to bear in the context of vaccine development. Suzanne, let me turn it back over to you for a Menti question. That is, do you feel that modeling simulation adds value to vaccine development? This is very early days, and pharmacometric support is a relatively scarce resource. Should we be spending our time working on this, right? Is this an area where my suspicion is we have a great deal of low-hanging fruit and some very simple things that we know around that work in the context of model-based drug development can easily be deployed in the vaccine space. That's my own particular bias, but I wanted to hear from the larger group. All right, that looks convincing to me. I won't run the stats on what 8 respondents out of 8 means, but it sounds pretty convincing. Suzanne, let's have the ball back again, and let me walk through some acknowledgements. I'd like to thank the Maternal Influenza Immunization Data Analysis Working Group. Again, that's really formed under the unique umbrella of the Bill and Melinda Gates Foundation, where you've got a great deal of investigators, global trial sponsors, regulatory functions all coming together to work towards a common good. And this work was supported by the Bill and Melinda Gates Foundation. Suzanne, maybe I can turn it back to you and we can move into the question and answer portion of the presentation.
Okay, thanks so much, Mike, for the very informative presentation. Looks like we have some questions from our audience. As Mike said, please feel free to enter them into the Q&A box, and we'll try to answer as many as we can in the time we have allotted. Mike, it looks like our first question from the audience is, what do you think is driving the long half-life of antibodies in young children?
Great question. The area that I think that would be most fruitful is to really go back over those palivizumab results. I mean, clearly, they're indicating there are covariate searches in that population pharmacokinetic analysis, like any other POP-PK activity. Clearly, they found body weight is important, so that's going to be key. And then gestational age. And again, I think that's extremely interesting. We know these antibodies are salvaged from being broken down into their constituent amino acids by FcRn, or the Bramble receptor. That is the antibodies from the early endosome that prevents them from being shuttled into the late endosome. So that's the thing that is giving these antibodies these very long half-lives. Same for albumin as well. My speculation would be that the FcRn, or the Bramble receptor, also known as the neonatal receptor, is upregulated. Right? There's just a higher level, higher amount of this receptor, and it is doing everything it can to salvage antibodies from metabolism. And again, speculating, these infants don't produce their own antibodies for many weeks, in some cases months. So you might imagine there's a survival advantage conferred to those infants if they hang on to mom's antibody for as long as possible. Give themselves enough time to produce their own antibody response.
Looks like we have some more questions. Someone wants to know, Mike, why do you think that modeling and simulation hasn't been utilized very much in vaccine development?
Ooh, great and loaded question, and I don't want to step on anybody's toes here. Why? So there's a couple of reasons. Vaccines are developed around the idea they have to be absolutely safe. So, the concept of pushing doses, supplying very aggressive adjuvants is very anathema to vaccine development. The other component is the idea of adjusting dosing schedule, which is something we do all the time in traditional drug development. I think that in people's minds that are developing vaccines, those schedules are set. Right, especially in the context of infants, which are a large population for a sponsor. We have child visits scheduled, and your vaccines have to fit into that dosing schedule. So I wonder, if there isn't a lot of appetite to assess risk, the classic therapeutic index that we do in regular drug development, and you have no opportunity or no perceived opportunity to evaluate schedule, what work is there to be done? I guess I would be concerned that that's kind of the mindset there.
All right. Someone would like to know, so in question number 2 in Menti, you asked the audience, were you surprised by the alignment of TIV and Tdap titer kinetics? And so one of our audience members wants to know what your speculation is to that question.
I think that we have a relatively small number of adjuvants that are available. Adjuvants are additional components that are added to the immunogen in the vaccine that are designed to spur immune response. Very typically, you might use alum in some of the earlier vaccines, and that really is just an aluminum ion that is designed to irritate the immune system and provoke greater uptake of the immunogen and greater processing. I wonder whether the choice of adjuvant, it could be important on the kinetics. In other words, the y-axis scale, how much antibody is produced. And again, we're very gun-shy about using potent adjuvants in a clinical case. So that may be putting kind of a ceiling on how much antibody is produced, as would presumably the body's own production machinery. In terms of the timing, when things rise, when things fall, I guess I was not surprised. Walking into this, I assumed that some portions of the features that we're looking at in the data are drug dependent, the vaccine, and some are system dependent, which in this case is the immune system, right? So I was not surprised that the two aligned relatively well. What I was surprised about is when I tried to go and comb through the literature to find other kinetic profiles, I had a really hard time. There was not a lot of data or information out there. And so this is, to me, really low-hanging fruit, right? Coming up and understanding if we can pull together a database of this information. Do we see the same kinetic pattern? And if we do, that's really interesting news in terms of how ACIP and other recommending bodies would put forward recommendations.
Mike, can you discuss what do we know about the placental transfer of antibodies?
Yeah, that's complicated. At the beginning, I highlighted a couple of things that are important to us. So that's maternal levels and gestational age. Placental integrity is important. So if you have a disrupted vasculature system between the infant and the mother, that is going to impede antibody transfer. There does appear to be a subclass preference. So for whatever reason, IgG1s are preferentially transferred over IgG4, over IgG3, over IgG2. And so this does appear to be an active transfer. This is a sort of a protected boundary. There's highly likely to be some antibody transfer just because of osmotic gradients, but this does appear to be an actively transferred system. In terms of timing, it looks to be relatively rapid. So you would expect the same kind of transfer speed that you would, say, the intercompartmental clearance for antibodies between blood and the peripheral tissue. We know that timing is important as well. So the majority of the transfer happens in the last 4 weeks of pregnancy. To me, that does suggest that you've got something that is beginning to be upregulated in those infants or that placental area to begin to pull those antibodies from mom into the infant, presumably in preparation for delivery when they're going to have to be out in the world on their own with only the antibodies given to them by mom. I hope that answers your question. It's a pretty complicated process.
One of our attendees wants to know, can you use the model that you developed for other B-cell mediated vaccines, i.e., could you borrow the estimated parameter values to inform your model for a new vaccine?
Yeah, and that would be my hope and intent. I did explain that the y-axis was really complicated, so I don't, unless the assay was configured exactly the same way for a novel vaccine, then the y-axis prediction in terms of their numeric units is going to be off. However, I do think that it's a very reasonable first effort to take this model in simulation mode and run out what that kinetic profile looks like in moms. Again, with the caveat that the y-axis is probably going to be different. But it does suggest that if you want to know, if you're perhaps looking at different adjuvants and different dose levels, the sampling schedule, you probably want to vaccinate and then get a sample at 6 to 8 weeks, 6 to 9 weeks after vaccination. That's highly likely, if this model bears out, to be the time at which you get maximum antibody response. And if you're looking for a dose response or an adjuvant response as a way to discriminate which form of the vaccine you want to take forward in development, that seems like a natural place to be leveraging the model to assign a sampling schedule, for example.
Mike, it looks like we have one final question from the audience. What would you do to dissect the heterogeneity in the maternal antibody kinetic profile?
Yeah, great question. And the fact that that question is even being asked is important, right? And how would I address it? Well, I've got a hammer. Things look like nails. We do this all the time for POP-PK and POP-PD analysis, right? You start with a base structural model that describes the population behavior. There's a great deal of variability in the population. And then you work through covariates, which components of the model seem to be affected by different demographic features. I didn't show that here, but for example, in that South Africa trial, there was a significant subgroup of pregnant women with HIV. And that HIV covariate is very important in the kinetic profile in mom. HIV-infected mothers have a longer lag between vaccination and maximal titer value, right? So something suggesting that something is more sluggish in the immune response. And they also have a lower peak titer, suggesting that the magnitude of the response to the vaccine is quite a bit lower. Right, so just as we would carry out any other covariate analysis in normal pharmacometric activity, this is an area where we can really add value to vaccine development by identifying subpopulations that have a meaningfully different vaccine response. And then we can ask the same kind of questions we do in traditional drug development. Is that difference sufficiently large that I need to do something about it? Do I need to give a higher dose? Do I need to revaccinate, or is the difference relatively minor, and that's okay, right? So the same approaches we use in, which sounds like a simple answer, that really hasn't been tested, used in the context of vaccine development.